Okay, everybody. So, we're going to continue talking about the various things that we're interested in. Okay.
We go the homework though?
Sure. Before we do that, let's start going over a basic concept here. Okay. Smartboard's working this morning. All right. Fine. Okay. So before we go over homework questions, let's tackle how to solve a differential equation. Okay. Okay. Whew. So far we've seen differential equations. We've seen them basically in a form of verified, the given solution works for the differential equation, etc. So we're actually given all the equations we need. But often we have situations where we're not given the equation. We're just given a differential equation and asked, to simply find a solution to it. Okay. So so basically, an example of this might be something like y prime equals, make sure I write this one down, 2x over y. Okay. Yes. Okay. 2x over y. And we might say, come up with a general solution for this. Okay. We'd have to figure out some way of doing so. Okay. Now, what do you think I want to do if I'm asked to come up with a general solution? Okay, so you're thinking of integral, okay, and that's right. But so far, or rather, what we know how the integral works, it only works really for just one variable at a time. So if I tried to integrate this right now on both sides of the equation, I'd run into a problem over here because I got the y in the bottom. Okay, I don't want that. So what do you think I'm actually going to do?
Solve for what?
Not solve for y, but get everything with a y on one side and everything for an x on the other. Okay? In this case, it's fairly easy. What do I do? Or multiply both sides by y. And that would give me y times y prime is equal to 2x. Okay? Technically speaking, okay, y prime is just y prime is really just dy by dx. So if I wanted to, I could substitute that in. Okay. Oh, nope, because it's y prime. It's not, okay? And then, also 2 would be y squared. Why do that? Okay. But the reason I'm doing this now is because what am I going to do with this dx? I'm going to move it over to the 2x side, right? Okay. So that way everything with an x is on one side, everything with a y is on the other. So that will give me y times dy equals 2x dx like so. Okay. And now, if I want to come up with a solution to this, I can integrate both sides. This side I'm clearly integrating with respect to y. This side I'm clearly integrating with respect to x. Okay, so it should come out nicely. What would the antiderivative of y be?
2y squared.
Okay, so it's not 2y squared. It's
2y over 2.
Okay, not 2y over 2.
Y squared over 2.
Y squared over 2. Okay. And we'll go ahead and write the plus. We'll say plus c sub 1. Yeah, you're just using the standard reverse power rule, anti-power rule on that. Okay. Well, okay, that's y to the first, right? So integral tells me I add 1 to the exponent and divide by the new exponent. Just because it's y doesn't mean it's not going to work. Yeah, it's the antiderivative. That's what the integral means. Yes, everybody. Integral, antiderivative, they're the same thing. Okay, they're synonyms. So when you see that, when you see an integral sign, just start thinking antiderivative.
Why did you call it C1?
You will see here in a second. Because on the other side there'll be a constant as well, right?
What was the original? No, they're not the same.
why should they be the same?
For y
Okay.
and x.
Yeah, it was at the very top. The original problem we started off was solve basically y prime equals 2x over y. Okay? And so here are the steps involved so far. Okay, we separate our variables, got it down to here. Okay? So we integrate the y side, we integrate the x side. That one should be easy. It's going to be what?
X
X
squared.
squared.
Just x
plus
squared. Okay? Plus, we'll call it c2 this time. Okay? Now,
Why not x squared over
The 2 cancels that out.
2?
the 2's cancel. Because
Oh.
it's being 2x squared over 2, and the 2's cancel. Okay? Alright, now we want basically this to be as close to y equals as possible. Okay? So we're going to go ahead and shuffle things around. We're going to move the C1 over to here. Okay? Now, okay, C2 plus C1, okay? What do we know about them? They're just what?
Constants.
They're
So
constants.
that gives you a c, right?
So they could just equal any random constant C, right? And it won't matter for our problem. In fact, because we're looking for a general solution, we want them to be equal to any random C, okay? And so C2 minus C1 is just C, as far as we're concerned, okay? And in fact, when you do these things, from now on, and so that's our answer to the differential equation. But when you do these things from now on, you won't have to write out the both plus c's. You can just write the plus c on the x side and be done. Okay? Everyone got that?
Why'd you have to
We're
go
gonna
through
multiply
that
by
whole
2.
process?
Okay, sorry?
That's you can just leave it like that?
Yeah.
You don't have to multiply by 2 and
What would I multiply by 2?
this is y squared over 2.
The y alone is more.
Oh, yeah, you can leave it alone right here at this point, yes. And if you really wanted y by itself, you could do a few more steps,
you
but
don't have to do it.
you don't have to. At this point, we're done.
Why did you go through that whole process at the C so we can just go on straight from there?
Just to illustrate what happens, because you're so used to, when you have an indefinite integral, putting a plus c on the end, I want to demonstrate why it doesn't matter to put the plus c on the y side, because at the end it just comes out to just a plus c anyway. Okay? Alright, so this here now, okay, is the solution, the general solution to y prime equals 2x over y, okay? Now, if I wanted to confirm that that's the general solution, what do you think I could do? What do you think I should do?
Plug in like a number.
Go backwards. So what does that mean I'm going to do?
Take the derivative of it.
Take the derivative of my answer. If I did that, if you're ever wondering, gee, did I get the right thing? Well, take the derivative of your answer. And realize when you're taking the derivative here, it will be implicitly, okay? So we have y squared over 2 equals x squared plus c, okay? We're going to take the derivative of this implicitly. What's the derivative of y squared? 2y, y prime, okay? So 2y, y prime, or dy by dx, doesn't matter what you use. It's still all over 2.
And dy dx is the same.
Yes,
I
they're
thought if you're taking the derivative of
okay.
y, then you don't need to add the y prime to that.
No, you always have to, okay? So this is what you get right here. Now what's going to happen to those 2's? They cancel. Y times y prime equals 2x. Divide both sides by y. We get y prime is equal to 2x over y. So, via the derivative, we can show that that is indeed the correct answer. Okay? So, that's the general solution. Now, how you would find a specific solution? Well, in order to find a specific solution, you would have to have been given an x or y value to start with. Actually, in this case, both an x and a y value. Sometimes, depending on how the problem is written, you can get away with just the one value, okay? Or if you're told, excuse me, something about y prime and y, or y prime and x in the beginning, you can figure out the other one. But this particular problem here, you need both x and y, okay? So, how you would do that is, if you were just given a random point, let's say at the beginning up here, you were told, solve this when x is equal to 3 and y is equal to 4, okay? When you come down here, after you find your general solution, okay, you will plug in 3 and 4 for x and y respectively, okay? So our general solution is this right there. Our specific solution, okay, would be just putting in the given points into this thing. So it's going to be, y was 4, so it would be 4 squared over 2 equals,
That's fine.
yeah, equals 3 squared plus c, okay? And then we're just solving for c at that point, okay? So it's 16 over 2, which is 8, equals 9 plus c. So we're going to have -1 is equal to c. So we figured out what c was, but that means our specific solution, when x was 3 and y was 4 for this particular problem, would be the specific solution would be y squared over 2 equals x squared minus 1 under the given conditions, okay? Now, again, if you're not given a point, you're not given any numbers, obviously all you can do is go to a general solution, okay? But when you want a specific solution, they'll give you numbers. The problem will have something like that involved for you to solve, okay? Everyone see how this works?
You're done.
Yeah, sure. Yes, Jazz.
If it had said when would you see it as f of 3 or f of 3 equals 4? How would you say when the specific solution equals that, or when?
Oh, it will say, basically, I guess if they're asking how you know to find the specific solution, it'll basically say solve the differential equation when, this, or with the given values, or something like that, okay? And they could do f of 3 equals 4. Actually, they're more likely to do y of 3 equals 4, okay? Because we're doing things in terms of x and y here, okay? But yeah, they could certainly do that, okay? Oh, did that answer your question?
Yeah.
Okay, good. All right, so this is how you would solve a differential equation, okay? Any questions about that so far? All right, good. Notice what I did there, okay, was I had my x's and y's together on one side, and I moved them apart so all my x's are on one side and all my y's on the other. That sort of notion is called a separation of variables, okay? Okay? Basically, a separation of variables just means you separate the x's and y's in a differential equation, okay? And we're going to be looking more at how to do this when we get back from Long Winter Weekend. Okay, because it can become, the separation of variables can become very tricky. The one we did was rather easy, right? Okay, all I had to do was shuffle over a y, okay? But, they can get much, much, much more difficult. For example, if I wrote up something like x squared plus 4 dy is equal to xy dx, that's a lot so clear-cut on what I'm supposed to do, right? You guys can probably figure it out. What do you think I'm going to do on the this side over here? I can divide everything by x squared plus 4, right? Okay? And over here I can divide everything by y, and that will separate them, okay? But it wasn't clearly as easy as it was in the previous problem. It was just, we just move the y over, okay? In this case over here, we're having to do multiple steps. And so here, rewritten, this thing becomes dy over y, which is fine, equals x dx over x squared plus 4. And now when we solve this particular equation, okay, we solve them using whatever regular integration rules we've got. So on this side over here, dy over y, well, I take the integral of that. What would that become?
Natural log.
Natural log of y. Okay? Because it's basically 1 over y. The integral of 1 over something is a natural log. Or 1 over a constant. If it's got a power, you can do the reverse power rule to it. Okay? Over here, though, what would I have to do?
You have to do
What happened to
That'd be
that
like
x
an
squared
arc
plus
function.
4?
Okay, not an arc function.
Rod.
Okay. If there was no x up there, it would be the arctangent I would use here. Okay. But there's an x up there. Okay. So remember, the arctangent works when I've got when I'm taking the integral of dx over a squared plus x squared. Okay. I'd have an x squared, got 2
When you
squared.
separate the integral, you have like x over
Yeah,
x
could you
squared plus-
separate the integral and then do the arc?
I could do that, but I don't actually have to do things that complicated. Okay. What's the relationship between x squared plus 4 and x?
Wait, where is he?
Okay, x is the derivative, right? Or 2x would be. So this is actually a substitution, right? Yeah. Okay, this would just be a regular old substitution. I would just add a 2 up here and put a 1/2 on the outside, and then be able to do it. Okay. And so that would be my final answer. I'm breaking it apart. Okay. All right. Any questions there? The book actually takes us way further than this right here, because they want to get rid of the ln on the one side.
So that's why sometimes when I check the answers in the book, they're just like ridiculous.
Yeah, and that could be the case because they're taking it way further than we do. Okay, sometimes. All right. But this is what you would get right here. Okay. And so, for me, you wouldn't have to go necessarily any further than that. Okay. But as you can see, okay, from this example here, you've got these problems that get rather complex quickly because you can have several steps involved. We started off with a differential equation that was all mixed up. We had to unmix it. Then we had to take the integral of it. And then when we took the integral, regular integration rules apply. Okay, and we ended up having a u substitution situation. By the way, what I did up here, adding the 2 and the 1/2, and not doing the whole process of saying u is equal to this, du equals to this. If it's something easy like that you can just recognize off the bat, feel free to just go ahead and do what I did. Okay, you don't necessarily have to rewrite everything in terms of u. Okay, in fact, for these types of problems, you probably don't want to do that because you want the answer to come out at the end in terms of x, not u. Okay. Okay. Any questions about how any of this works? Okay. So it's essentially, and if I took the derivative of that, I will get what I started with at the beginning. Okay. All right. There's no further questions about this stuff here. Let's go ahead and look at your homework questions that you all said you had. Okay. Because this would be a good place to stop before long winter weekend. Okay. So homework questions.
Mr. Dowell, I have one question.
Uh-huh.
The one that you just did,
Yeah.
the reason you don't add the plus c on the lny
Uh-huh.
is because you have them, right?
Yeah. Basically, again, you could add the plus c constants to both sides. It's just that as you work things through, you're just going to combine them anyway into one constant on the x side. Okay? And so that's what happens. I mean, basically, I could have gone through here
Right.
and just put I could have said that's plus c1 and that's plus c2, but then the very next step, I move that c1 over,
Right.
and c2 minus c1 is just a constant. We don't really care. Okay?
Why did the constants have to be on the same side?
Oh, why did it have to be on the x side?
Yeah. Do they?
No, but we'd like them on the x side. It's because ultimately, the reason we like them on the x side is because a lot of times you won't necessarily stop at a step like this right here. You'd keep going, and so you would keep going and have like the plus, you have y equals stuff, okay? And in that case, you don't want the plus c on the y side because you're just trying to get y completely by itself. We don't have to do that fully for every problem, okay? Or we don't have to do that in every question. In fact, the next steps here to get y by itself, they're not very pretty, okay? What you would do is you would essentially use properties you know about of logarithms, move that up and make it the exponent of that there. So you would have, so this thing would become natural log of y equals the natural log of the square root of x squared plus 4 plus c. Then to get rid of the natural log, we take everything and make it an exponent of e. That's how you get rid of natural logs. So
would we have to keep doing those steps?
Generally, no. Okay. Most time on the AP, you don't have to do all these steps. Okay. But the book actually did so, and so what happens here when you do this? Those cancel, so this would become y equals. This would cancel everything except for the c out in front there, so this becomes e to the c root x squared plus 4, like so. And really, I believe at this point.
Is it addition
Well, you could say it's plus or minus because obviously there's the square root there. Okay, but e to the c is a what? It's a constant. So you can actually make this. Just replace the e to the c with a constant, and you can leave your answer. And so that's taking the answer as far as you could possibly go with this. Okay. But you don't, again, that's not necessarily needed. You don't necessarily have to do all that, okay? I would be perfectly fine, and the AP generally is perfectly fine unless they say otherwise. And they usually don't. They usually just have you stop. This step right here is usually good enough, okay? Where you wouldn't have to do everything in terms of the natural log, okay? Do you have to do that sort of natural log manipulation, Diego? Yeah, you should know that. Okay? So if you need a refresher course, we can go over that at a later date. But it's absolutely the case. Okay? All right. Which one?
37.
37. Okay. So is this the one C1 science 3, or am I on the wrong page?
Yeah, that's right.
Okay. All right. So we want to verify that the general solution satisfies the differential equation. Didn't find the particular solution that satisfies the initial condition. Okay? So, all right, yesterday we saw how you verify by simply just taking the derivative of the general solution and seeing if it equals what you got. Then, to find the particular solution, the initial condition is given to you. It's basically going to be what those values are. Okay? And so you just have to manipulate things according to that, okay? So, we've got y is equal to c1 sine q of 3x plus c2 cosine of 3x. And we're told that y double prime is plus 9y is equal to 0, okay? And we're also told that we want the general solution, or a specific solution, excuse me. I'm going to write this up here. So we want specific solution when, if basically, when y is equal to, what's it? Sorry. 2. X is equal to pi over 6, and when y prime is equal to 1, x is still equal to pi over 6. Okay? Okay, so there we have it. All right. This one I could, undo that. This one right here I can tell you is going to take some extra steps involved, because we have two unknowns up there, okay? What happens when you have two unknowns in an equation?
Twice as long.
Put them on different sides.
Okay. Well, for example, if I have two unknowns and I'm trying to figure them out, how many equations do I need? Two equations. Okay. That's why they gave you when y is equal to 2, x is pi over 6, and when y prime is equal to 1, x is equal to pi over 6, because we're going to use that fact up here when we start doing things. But the very first thing we have to do is verify that this indeed is a solution to this. Okay? So the first thing I need to do is I need to take the first derivative and the second derivative. Okay? What's my first derivative going to be? Okay?
So you're trying to prove that first
Well,
one.
the C's go away.
Okay?
It'd be cosine.
All right, guys. All right. So many people talking at once.
Cosine
Hold up.
3x.
What are you asking?
You said you're supposed to be trying to find what the first.
Yeah, so basically, we were given a differential equation right here, y double prime equals 9y is equal to 0. And the very first step in the problem is we need to confirm that that's true. Okay? And in order to do that, I've given y, so I need y prime, then I need y double prime.
And what is?
That's going to be for later. Okay, we're going to use that after we're done with this. Okay. Did you have a question, or you just... Okay. Now let's go through it. All right. So, what's this going to be here? You were saying it?
3 times sine 3x.
Okay, so 3,
Cosine.
Or cosine.
and is it just 3?
Negative
C1 cosine of 3x.
C1 doesn't go away.
No,
Nope.
the 3 goes away, right? You took it out, put it in the front.
Oh, no, it doesn't go away. It's a chain rule. The sine of 3x's derivative would be 3 cosine of 3x. Okay? Or cosine of 3x times 3.
C instead of C1 since we didn't learn that.
Nah, but we got 2 of them this time.
But why
There's
does
different
C
constants
stay?
here. Because it's a constant out in front.
Take a coefficient.
Oh,
It's like a
right,
coefficient.
okay.
Okay? So it just doesn't go away. And the same thing goes, so we're going to do this side over here. What's the derivative of the cosine of 3x?
Negative
C.
Negative sine of 3x times 3. And when we put it in here, it becomes minus 3 c2 sine of 3x. Okay? That's our first derivative. Okay? Now, our second derivative based off of this,
we take out the
6C.
we could take out the 3's, but we don't. I mean, it's not going to really help us all that much. It would be 3c1 times 3 times minus the sine of x. Okay, so minus 9c1 sine of 3x. Okay. Derivative of the sine is cosine, so it would be minus 9c2 cosine of 3x. And will this combine with 9 of these? Will they cancel each other out?
Yeah.
Yeah.
How did you just change it to 9?
Okay. There's a 3 out in front here.
Yeah.
Derivative of this is a what? It would be minus the sine of 3x
Right.
times 3, right?
Oh, so that's
Three
the second derivative.
Yes.
Oh, sorry.
Yeah,
Why?
You didn't put
Can
the
you put the
second
mark on the second one?
Oh, I did. I'm sorry. I didn't see what it did. Better? There we go. Okay. So, and we can clearly see that that's going to work. That'll make this thing work. Okay. Because this is the negative of this, except it's got 9's in front of it. So if I multiply the top by 9, they would cancel it out. Okay. So I know that's true. Okay. All right. So this is a differential equation. Now what we want to do is we want to find the specific solution. But we've got 2 constants in here, C1 and C2. Okay. So I'm going to have to kind of treat this as I would a, what do you call it? A multivariable equation with 2 unknowns. So 2 equations with 2 unknowns, okay? So I could do that with either using methods from Algebra 2, I could do it with substitution, I could do it with elimination, I could do it good old-fashioned solve for y, or things like that. This is not going to be so bad because the sines and the cosines will actually go away. We're told in the beginning that when y is equal to 2, x is equal to pi over 6. So our first one is going to be 2 equals c1. The sine of 3 pi over 6, which is pi over 2, right? What's 3 pi? What's the sine of pi over 2?
1.
1. Okay, so we get c plus c2 cosine of 3 pi over 6, and which is pi over 2. What's the cosine of pi over 2? 0. So that side actually goes away. So we're actually told that so from that we actually directly solve that c1 is equal to 2. Okay? Does everyone see how that worked? Again, I'll write it all out, okay? Why this is the case? It's because 2 is equal to c1 sine of 3 times pi over 6 plus c2 cosine of 3 pi over 6, okay? Which would be 2 c1 sine of pi over 2 plus c2 cosine pi over 2, which is 2 equals c1 times 1 plus c2 times 0, which gives us that 2 is equal to c1, okay? So, that's how we figured out the first one. Now, we're also told that y prime is equal to, that when y prime is 1, I forgot, x is equal to pi over 6. So y prime is given to me, it's this one up here. So I'm going to go ahead and use that one as well. So it'd be 2 is equal to, the second one is going to be that 1 is equal to c1 cosine of 3, sorry. I'm leaving off my 3's.
What is that pi over sine pi over what?
2.
So we just plug in 2 for C1 and so.
Uh-huh. Well, we don't necessarily, we could plug in the 2 here, but we don't need to, because as you're going to see here, okay, okay. Now, that's a
That's the
3.
second derivative.
It's the first derivative. Because that's, okay. Now, what's going to happen to that right there?
0.
It's 0 again, so all that goes to 0. This is what? It's 1 again. So we would have 1 is equal to negative 3c2, negative 1, sorry. Divide both sides. Was it positive 1? It's positive.
It's positive.
Yeah, it's positive 1. Okay. So that gives me minus 1/3 equals C2. Okay?
Where'd you get the, can you scroll up real quick?
Yeah.
Where'd you get the minus 1 over there? All the way on the left.
Oh, I think I added a minus sign in it when there wasn't one. Yeah, it was this minus sign right here. It's supposed to be a plus 1. Okay. So that was my bad.
How did y prime cancel out each other? Or did y double prime to get y double prime plus 9y? Or,
Oh, that was just the given differential equation.
but I mean, we figured it out, or we did the second derivative, but then we had sine minus cosine. So
Right. So if you look up here, this was the given differential equation,
yeah,
and we wanted to show that this up here was the solution to it. Okay. So we took the first derivative, and then the second derivative. Well, the second derivative is basically 9 times minus c1 sine of 3x minus c2 cosine of 3x, which is literally this up here
Oh, yeah.
with the signs flipped.
okay, yeah.
And so that's why it became fairly obvious that it would just be, what was it? Scroll back down.
Yeah, just do that.
Okay.
So basically when you said one specific solution for, all you do is plug in the points and see
Yeah.
what it
Yeah. Okay. And they usually give you, if they're asking for a specific solution, they give it to you. By the way, technically speaking, even though I found that C1 and C2, what they were, I'm not actually done until I write the full out specific solution. So in order to actually be fully done with my answer here, I really ought to write out here that y is equal to 2 sine of 3x, what is it, plus,
Plus cos.
so it would be minus 1/3 cosine of 3x. And so this is the full out specific solution. Okay? And again, they will, so when you're when you're doing like if this was an AP problem, which by the way, this would actually be a fairly good,
A full AP problem.
yeah, this would be a full, yeah, they would, you can see this sort of thing appear on an AP test. In fact, last year, one of the free response questions was basically exactly like this.
What's the format of the AP? Like how many multiple choice? How many?
It varies slightly every year, okay? But typically, there's about 60 multiple choice questions total, divided into a non-calculator and calculator section. So the calculator part is usually shorter. So it would be like something like maybe 30 or 35 non-calculator multiple choice and like 20 calculator multiple choice. And then you've got 2 free response sections, again with calculator and without calculator. And again, it varies how many questions are in each section, but typically there's 6 to 7 free response questions total.
For each section or?
No, just in total. So you could have like 3 with calculator and 4 without, or 4 with a calculator, 3 without, that sort of thing. Okay. The free response questions are 15 minutes apiece, time-wise. So it'll be like section 2, calculator, answer the following free response questions. You have an hour. There'll be like 4 questions that you can answer. Okay. Multiple choice questions, typically, they typically come out to be upwards. They can be upwards to 2 minutes per multiple choice question. So they're very generous on that. Do you need the full 2 minutes? No. Most of the questions you can answer like that. Okay. If you know what you're doing. A lot of them, there's no like. It's also not like the SAT where there's some sort of where there's tricky math involved, where they try to trick you with things. I mean, it's very direct. I mean, it's like my multiple choice questions. It's what's the derivative of this? What's this? What's this? Etc. Okay. I can tell you too, the non-calculator part of the free response and the multiple choice typically are more theory-based questions. So there'll be things like, do a, explain why, this is a critical point, or, do X, Y, or Z, or basically use the limit definition to find a derivative, that sort of thing, okay? While the calculator portion tends to be stuff you really just can't do without a calculator. So basically just interpreting graphs, things like that, okay? We'll go over a lot more AP questions when the time comes, okay? And we're on pace right now to basically spend all the spring from when we get back from spring break to May preparing for the AP.
Are we going to take any tests or should we
We'll take tests, but they'll be like AP-style review tests, okay? Because I gotta have grades for you. Okay? Plus, it's good practice. Sitting down, doing these things. All right? Okay, were there any other questions from homework? All right. Any questions on differential equations in general so far? Okay, this is a good stopping point, so I'll let you guys